Okay, hello everyone, and welcome back to Qubit by Qubit. We are on week number 14 of the Intro to Quantum Computing course, and today is going to be all about the Bloch sphere. So as a reminder, sort of where we're at right now, the last 3 weeks, I guess at this point, have been all about quantum physics, right? So sort of the more fundamental physics. We've looked at the double slit experiment, we've looked at the Stern-Gerlach experiment. In the last lab, we looked a little bit at eigenfunctions and modes of strings and how that relates to confinement and quantum systems, all that kind of stuff, which is all super interesting. I think it's kind of mind-blowing. But now we're going to take a bit of a step away from the physics and back to the quantum computing. And this is the beginning of the end of the course, I guess. This is the last real push toward how you use Qiskit, how you use IBM's quantum experience, and how you actually start programming a quantum computer. Now, we have seen the Bloch sphere before. It was one of the optional contents from a previous lab. I think it's also been covered in some of the lectures. But today we're going to take a dedicated hour to go through it and make sure that everyone's very familiar with how it works. So let's go ahead and get started. So the quick program for today, I have one logistical note before we start. Then everything else pretty much looks the same. We'll have our attendance quiz, pre-lab Zoom feedback. One question that's kind of not really from last week, but it did come up a lot just in preparation for this week's material. So we thought we'd address it hopefully before it becomes a common question. And then we'll have the actual lab content and the post-lab Zoom feedback. Okay, so quick logistical notes. This is just a reminder. Nothing here is new. So if you're already familiar with the student assistant office hours and the Friday homework review sessions, there shouldn't be anything here that's different. It should all be exactly what you have seen before. So the student assistant office hours are there to basically be yet another time for you to review lab material and potentially walk through homework problems. So you'll notice that we never explicitly do homework problems in the labs. If you sit down on the homework and you realize that you really are struggling with some of the problems, I would highly recommend the student assistant office hours, because you can sit down with them and go through the exact problems that are on the homework and how you should do them. So the Zoom link for that is available on Canvas. It is entirely optional, of course. It's primarily there as a resource if you feel you need extra help in any particular week. The second one, maybe I'm kind of confusing these, but the second one is the homework review session, which is another opportunity to go through the weekly homework. This one is only held for 1 hour, though. So the student assistant office hours are meant to be available sort of like at many different times so that hopefully everybody can get to them at some point. The homework review sessions are a little bit shorter, but the recordings are available if you cannot attend live. So again, both of these things totally optional, but you can find the links on Canvas to attend them live or to watch the recorded version for the homework review sessions. Now, last note here that is an important one to, I guess, highlight is that you this week should be creating your IBM Quantum Experience accounts. So the instructions for this should be on Canvas, and you are free to ask questions about it. I'm actually not sure if you should post on Piazza or send to the email. I'll say for now, post on Piazza if you have any issues with this, and we'll try to help you. But the reason we want you to do that this week is because it is just setting up an account. It should be pretty straightforward, but there are lots of little edge cases and things you might run into. So we just want to make sure everyone's set up on it properly before we get into using it next week. Because next week we will actually start using it. We hope that everyone will have their accounts set up by then. Before I forget, I'll turn on the chat. So if anybody has questions as I'm going through these logistical things, feel free to throw those in the chat. Okay, so let's do the Canvas attendance quiz. So log into Canvas. The lab number here is 1, of course. Today's quiz password is 4758. I don't know what the question is, as a matter of fact. I guess they filled it in. The attendance quiz. Oh, the quiz itself is empty. Okay. Interesting. Well, I thought they were gonna fill in a question and I just wasn't aware of it. But I guess there's no question this week. So even less work. Hey, I guess just make sure you do submit it. let me know if, yeah, as long as you can still submit it and show that you're attending, I think that's the thing that really matters here. Cool. Okay. I guess I'm actually not that out of the loop. It really is blank. Okay, awesome. So let's do the pre-lab Zoom feedback. So same question as always, scale of 1 to 5. How would you rate? Oh, whoa. Interesting. It showed the poll thing on my screen share there for a second. Anyway, yeah, so same question as always, scale of 1 to 5. How did you feel about this week's content? Go ahead, fill this out. I'm also trying, by the way, to remember to share the poll results. Just to be totally clear, the results are totally anonymous. So, don't worry about somebody seeing which answer you picked. But I will share the aggregate results just kind of for curiosity, so you can see what people are answering. Okay, so as people fill that out, oh yeah, we go on to this. Okay, so I'll leave this up actually as I do the question from past week. Now, this is not exactly, as I said, a question from last week only. This is a question we've gotten actually quite a bit at various points throughout the course, and that is, what is phase? So we talk about this thing called phase a lot in quantum mechanics and quantum computing, and specifically we have these two terms, global and relative phase. So global phase and relative phase. And as you might guess from the names, they are related, but it's very important to understand the difference between these two concepts. Now, I think that a really good analogy for this is to think about a clock. So if I show you this clock, right, I could ask you the question to describe where the minute hand is, right? And probably for most of us, we would describe the minute hand as being on the 2. That sort of seems like the easiest way to describe it. Now, a totally valid alternative way of describing it is to say that the minute hand is pointed toward the top right of my screen, right? And that gives you, roughly the same information. I could give you more information to make it more detailed about exactly where it's pointing, but roughly speaking, the minute hand is pointing off toward the top right of the screen. Okay, so what is the difference between these two ways of describing the hand? Suppose I rotate the entire clock face by 90 degrees, right? And now I ask you again to describe where the minute hand is. One of our descriptions changes, the other does not, right? So it's still accurate to say that the minute hand is over the 2 on the clock face, because when we rotated the clock, the entire, the numbers on the clock face rotated with us. And so the minute hand is still over the 2. But if I use the other description where I said, over here, it was pointing to the top right, over here, now the minute hand is pointing toward the bottom right. So that description changes. Now, this difference between sort of one description that changes when you rotate and one that does not is essentially the difference between global and relative phase. When we have a global description of an object, so for example, that this hand is pointed toward the top right of the world or my screen or whatever, that is a global description. And if we change the entire object, our global description can change. Just saying that the minute hand is over the 2, however, that's a relative description. It's relative to all the numbers that we see on the clock face. And so if we rotate the minute hand and the clock face together, the relative description doesn't change. Now, when we're telling time, the thing we care about is the relative position of our clock hands. Even though it would be kind of weird, if I hung a clock on the wall looking like this, it would take you a second, but you would still be able to figure out that the time here is 10:10, right? Rotating the clock doesn't actually change what time is on the clock face. The only thing that changes the time on the clock face is when you move the hands around. So if I moved, the minute hand up to the 12, that would change the time. Now, the exact same thing is true in quantum computing. If you have relative phase and you change the relative phase of a quantum state, and I'll show you what that means in a second, but if you change the relative phase, the quantum state does change, right? Just like saying the time changes. But if I change the global phase, which is kind of like just rotating the whole clock, nothing actually changes. The state is going to look a little bit different, but it holds the same information. So here the time doesn't change. Okay, now in the world of quantum mechanics, what these things actually look like is exponentials, so complex exponentials. We've seen those before, and we will return to them later in the lab. But suppose I had a state like 1 over root 2 ket 0 plus 1 over root 2 ket 1. Now, I could multiply the whole thing by some complex exponential like this. Doesn't matter which one. But if I multiply the whole thing, that's kind of like rotating the whole clock face. So even though the actual numbers here are going to change a little bit, the information in this state, the actual physical quantum state, doesn't change at all. So you'll often hear quantum physicists say, oh, global state doesn't matter, or sorry, global phase doesn't matter. Global phase doesn't change our quantum state. This is why, because when you multiply the whole thing by a complex phase factor, it's like rotating the whole clock face. The hands still stay on the same numbers. Let's contrast that to a relative phase. So a relative phase is when you multiply by a complex exponential again, but you only apply it to one of the two superposition states. So for example, I could do this. So now I'm not rotating the whole thing anymore. I'm not rotating the whole clock. I'm only rotating one of the hands. And so this is going to change the time. This is actually changing what physical state we are looking at. So this is a really important distinction to make in quantum computing. Oftentimes you'll see people just randomly start multiplying a whole quantum state by some phase factor. And the reason they're allowed to do that is because a global phase does not change anything. It's like rotating the whole clock. So let me quickly go to the questions just to see. Okay. I think none of that is entirely related to, to global and relative phase. Okay, so could I graphically show how global and relative phases work? Yes. We will get to that when we start talking about the Bloch sphere, because there is like a visual way of seeing it. Absolutely. Okay, while I think of it, I'm going to go ahead and share the results of the poll, the pre-lab Zoom poll, just so everyone can see that the majority option here is 4, which is great to see. But of course, we will still review everything in the lab. Normal distribution, indeed. Okay, so let's take a quick look at our lab content for this week. Basically, we'll have 2 halves, much like most of our labs. And basically, the way this lab is going to work is we're first going to talk about quantum states on the Bloch sphere. So a quantum state, as a reminder, is represented by a vector, right? So these are things like ket 0, ket plus, all that kind of thing. And the second half is going to be all about quantum gates on the Bloch sphere. So gates, as a reminder, are matrices, and they are things like the X gate or the Hadamard gate, stuff like that. The optional content for today is unrelated to the Bloch sphere, but is a little like additional note on the harmonic mode stuff we talked about last week. So if you stayed for the bonus content last week, this is going to be another fairly quick, probably 3 to 5 minute bonus section on Fourier transforms, which we will get to when we get there. Okay, so let's talk a little bit about the Bloch sphere. We have seen this slide before in, I think, the optional content of that previous lab. And it's a good way to think about why the Bloch sphere works and why we define it in the way we do. Now, I could ask you a question. How would you tell me where your hometown is on the globe, right? And you could tell me what your city name is or something like that. But if I wanted you to be really precise about where your hometown is, usually the way we describe precise locations on planet Earth is by latitude and longitude. Right, so some people are throwing it out in the chat there, latitude and longitude. Now, if you aren't familiar with these concepts, that's okay. I'll quickly review what they mean. Basically, what we do is we pick some reference point on the globe that's going to be 0 degrees. So I believe, actually, I'm not exactly sure where 0 degrees is. I know that the time zones start in Great Britain, but anyway, okay, we'll just pretend that the reference here is also Great Britain. I'm not exactly sure if that's true. But anyway, you pick some point on the globe that is 0 degrees. We're going to just call that one 0 degrees. Now, you can tell me which of these sort of vertical lines here drawn on the globe, you can tell me which of these vertical lines your home city is on by giving me a number of degrees away from 0, right? So the whole circle here is 360 degrees. You can just divide that up into even portions. And then I could tell you like, hey, my hometown is maybe 60 degrees away from 0, right? And that is fair. Now, once you know which line you're sitting on vertically, you also have to know which line you're sitting on horizontally. So maybe I sit on this line right here. And measurement of this works in much the same way. We pick a reference point, and then we describe how many degrees away from that reference point we are. So in this example, we could picture going from the North Pole here all the way down to the South Pole as being 180 degrees in total, right? So starting at the North Pole, going to the South Pole, there's 180 degrees in total. And then you can tell me where on that spectrum you lie. So if you're at 90 degrees, you're right on the equator. If you're less than 90 degrees, you're in the northern hemisphere. If you're more than 90 degrees, you're in the southern hemisphere, right? Now, this idea of using two angles to describe a location on a sphere is exactly what the Bloch sphere is. It's exactly the same concept. It's just dressed up to look a little bit more mathematical than how I just described. Okay, so yeah, people are saying Greenwich is the 0 degrees. Cool. Okay, so let's move on to the Bloch sphere. Now, this picture is going to come up about 500 times today, so we should get used to it and describe a little bit how to read it. Now, the Bloch sphere allows us to locate points on a sphere. So everything we're going to talk about today is points on the surface of a sphere, right? So for example, this one here is meant to represent some point laying on the surface of the sphere. And the way we're going to describe the location is with two angles, theta, which is this one, and phi, which is that one. So just like latitude and longitude, theta is going to tell us how far from the North Pole we are, and phi is going to tell us how far from Greenwich, in this case, we are. Now, it is important to get the directions on this right. So note that phi here is always the angle going, if you were looking at the globe from the top, phi goes counterclockwise around, right? So if I had a state that was out here, for example, that would not be 90 degrees, that would be 270 degrees, okay? So I want you to think for a minute about what the ranges of these angles have to be in order to cover every single point on the sphere. In other words, both of these angles can obviously start at 0, but what is their maximum value? How far do they have to go to cover every single point on the sphere? So think about that for a second. It's not the most obvious question. It's a bit of a trick question. Okay, so someone says 2 pi. That is correct for one of them. Right. Okay, so people are starting to get the idea here that perhaps some of them should be 2 pi, some of them should be pi, maybe some of them go minus pi to pi. So all of these are going to be valid answers, right? As long as you have something where one of the angles goes from 0 to 2 pi at least, and the other one goes from 0 to pi at least, then you can cover every single point on the sphere. Now, we are going to define a convention here, which is the following. Theta is going to be between 0 and pi. And this little symbol here just means contained in. So we're just telling you the range. This is the same as writing, this. Okay? And phi is going to be between 0 and 2 pi. So graphically, what that means is that theta can bring us all the way from the North Pole to the South Pole and anywhere along here, but it cannot go any further than the South Pole, right? Theta maxes out at just pi, which is 180 degrees. Phi, on the other hand, can go all the way around the equator. So phi goes all 360 degrees, all 2 pi radians around the equator. Okay, so I hope that, yeah, exactly. It's the same as spherical polar coordinates. So if you have learned that in like a calculus class, maybe, no worries if you haven't, but spherical coordinates is the exact same idea. Correct. So somebody just direct messaged me, the attendance quiz does not load. The attendance quiz is blank this week. Like there's no question you have to answer. You just have to make sure to submit it. So no worries if you don't see any answers on there, that's expected. Why theta can't be more than pi? Right, so this is perhaps something that's a little bit tricky to see. One person gave a good short definition or short description of it. If we allowed theta to be more than pi, let's think about what would happen, right? So suppose I allowed theta to go to 270 degrees. Suppose, right? This is not actually how it works, but suppose I did that. What problem would we run into? The problem we would run into here is that there's 2 different ways you could describe, for example, the y-axis, the negative y-axis. You could either describe it as, theta equals 270 degrees and phi equals 90 degrees, or you could describe it as theta equals 90 degrees and phi equals 270. So it's a little bit weird to try and see that, and I don't know if I can draw it properly. But if you allow these ranges to be larger, you end up getting duplicate descriptions of points on the sphere. So we restrict them like this just to make sure that every point, well, almost every point, has a unique description in terms of these angles. Okay. Any other questions? Thinking how to trace the full sphere using the values might help. Okay, yeah, that's a good point. So the way that I like to think about this is if I picked a slice of the sphere, for example. So suppose I draw some longitude lines like this, and I pick out just a narrow slice of the sphere. Basically, the way that these angles work is phi selects which slice I'm looking at, right? So this entire slice would have the same phi value or similar phi values, right? But the way you select where you are on this slice, if you're close to the equator, if you're close to the North Pole, close to the South Pole, that is going to be theta. So that's sort of the way that I like to visualize this is you have like a slice that you're moving around the sphere, and then theta selects where you are inside that slice. Okay. Yeah, so just to emphasize what I mean by this, and actually maybe I'll write it down so you have this on the slides too. This line here is what happens if we change theta and keep phi constant. So basically pick one value of phi, and then if you move theta, you would move along this line. If I had a line that looked more like this, somewhere on the sphere, let me just be very clear with what I'm pointing to. That's that line. If I did this line instead, that's what would happen if I kept theta constant and changed phi. Okay, so we are going to do some more practice with this, so don't worry, but I'm just trying to give you a really solid, I'm trying to give you a solid intuition for how the Bloch sphere works. Now, as somebody just pointed out here, the radius of these points doesn't matter here because all of the points are on the surface of the sphere. Therefore, they're all the same radius away from the center. So we never specify the radius of the Bloch sphere. Okay, so let me see. Yeah, this is another good point with counterclockwise and clockwise rotation. The way that I would recommend doing this is just to have a picture like this open next to you whenever you're doing a block sphere problem, just to make sure that you get sort of the directions of these angles correct. Okay, so why don't we go on and do some practice problems then? I think, I've talked enough about how this should work in theory. Let's see how it works in practice. So some general characteristics of the Bloch sphere. First of all, the Bloch sphere is a visual tool to show single qubit states. Now, every single point on the sphere of the Bloch sphere, on the surface of the Bloch sphere, represents a valid qubit state. And conversely, every valid qubit state maps to a point on the surface of the Bloch sphere. Okay, so if you pick a spot on the Bloch sphere, you always know it's going to be a valid quantum state. And if you have a valid quantum state, you can always draw it as a point on the Bloch sphere. There's a correspondence there. And I guess that's what the second point here says too. All single qubit states exist on the two-dimensional surface of the Bloch sphere. Now, these 2 points are going to become more clear in a little bit. So I'm just going to read them for now and not explain too much more. The angle theta gives us the proportions of ket 0 and ket 1 in our state. And the angle phi gives us the relative phase. So remember, relative phase is the important one. Global phase is the one that doesn't matter. Okay, and then final point, the Bloch sphere can be used to visualize qubit transformations. We'll see that in the second half when we talk about quantum gates. Okay, so some practice problems. Let's see we'll start off with very basic states and we'll build up to more complicated ones and what they look like on the Bloch sphere. Now, over the past couple of weeks, we have talked about the Stern-Gerlach experiment, right? As a very quick reminder, our electron has this thing called spin, which is an intrinsic property that gives it a magnetic moment or a magnetic field. You can think about it as. So I like to draw it as a little bar magnet with north on the top, south on the bottom. And we're going to shoot this electron really fast through another magnet. So here we have a magnet set up. Magnetic field lines go north to south. And we're going to fire this electron through that magnet. The attractive force on the south side is going to be stronger because the south side of the magnet is stronger. And that is going to cause this electron, for example, to deflect slightly up. So instead of going straight through the magnet, it'll deflect slightly up. Now, when you measure along the z-axis, we learned that there are only 2 possible outcomes. You can get spin up or you can get spin down. Spin up, we defined as being ket 0. And spin down, we defined as being ket 1. These are just definitions that we came up with. It just so happens that these have a very nice correspondence to the Bloch sphere because ket 0 happens to be the point at the very top, so like the North Pole, and ket 1 happens to be the point at the very bottom, the South Pole. Right? So visually looks very similar to the Bloch sphere, right? If you have an electron coming in the ket 0 state, it's going to deflect to the top. And if you have an electron coming in the ket minus state, it's going to deflect to the bottom. Or sorry, what did I say? Ket 0 is going to deflect to the top. Ket 1 is going to deflect to the bottom. And that's exactly what it looks like on the Bloch sphere. So this is sometimes how I try and remember where 0 and 1 are on the Bloch sphere. Let's look at another example. We also did the Stern-Gerlach experiment measuring along the x-axis, right? And so in this case, exact same setup. But now when we send the electron through, it will either deflect sort of to the right of the screen or it will deflect to the left of the screen. And again, we learned there are only these 2 possible outcomes when measuring along the x-axis. We defined spin right as being ket plus and spin left as being ket minus. Again, these were just definitions. And again, it just so happens that these conveniently show up in the same way on the Bloch sphere. The only trick here, I will say, is that you have to pretend you're looking at the sphere from this side. So suppose that you're looking at it from over here, right? So your z-axis is kind of up top, and your x-axis is off to the right. What happens then is ket plus appears on the right, and ket minus appears on the left. Okay, and again, that's how we did the Stern-Gerlach experiment. If it deflected to the right, we called it ket plus. If it deflected to the left, we called it ket minus. On the Bloch sphere, the arrow to the right is ket plus, the arrow to the left is ket minus. Okay, so let's think about one of the homework problems that appeared in the Stern-Gerlach section. What we did is we had an electron first go through the x-axis measurement and then go through a z-axis measurement. What we're doing here is we're going to keep all of the electrons that are spin right and discard, oh, actually, I'm sorry, I'm getting this wrong. Yeah, this is confusing. You do have to think about it as if you're looking from over here, right? And so again, if you're looking from over here, this arrow actually points to the left, and this arrow is pointing to the right. Is that clear how I'm getting this, like how you get the directions straight? It is a little bit confusing because the way we usually draw the Bloch sphere, it kind of looks reversed. Cool. Okay, so in this case, we are blocking out everything going to the right, and we are keeping everything going to the left. Okay, now I'm just noticing that I think actually we got ourselves confused when we were preparing these slides, because the next transition I'm about to activate says that we're keeping the ones going to the right. Yeah, so the drawing is just wrong. We'll go with it, but I do apologize for the confusion there. Now, okay, yeah, so let's just change it right here. I'm going to say that this represents spin right, and this represents spin left, even though the arrows suggest otherwise. So let's just say that the arrows are drawn incorrectly here. Okay. So we'll keep all of the ones that go to the right, and then we'll pass those through a z-axis measurement. Now, what you should have found on the homework problem is that when you do this setup, you still get 50-50 going up and going down. Okay, so why is that? The description for why that is that we gave is that ket right, so the ones that we're keeping, is equal to ket plus. And when we write ket plus in the z basis, and remember, all that means is we write it in terms of the eigenvectors of the z matrix, which are ket 0 and ket 1, we get this. Right? So ket plus is just a 50-50 superposition of ket 0 and ket 1. So when we pass it through the z-axis measurement, as expected, we get 50% ket 0 and 50% ket 1. Okay, so they go up and down. This is the full line of math that I was talking about. So we keep the spin right particles, which we define as being ket plus. That is equal to 1 over root 2 ket 0 plus 1 over root 2 ket 1. Again, this is just a definition. And this, if you use the probability postulate, you would see that it gives you 50% of the electrons going to 0 and 50% of the electrons going to 1. Okay, so we're going to compare and contrast this to an example on the following slide. What I want to point out, though, is where this state is. So here we were keeping everything going to the right. Okay, and so the quantum state that was being passed through the z-axis measurement is this one, ket plus. When we flip to the next slide, we're only going to change where this state is. Okay, so we're going to go from ket plus to now ket minus. So this arrow back here, it's meant to show that it's going on the negative z-axis. I know it can be a bit confusing, but that should be ket minus straight out back on the negative z-axis. Okay? And the only thing that we changed in our Stern-Gerlach machine is now we are going to block the spin right particles and let the spin left particles through. Okay, so now if we do the same math again, Instead of ket plus, we have ket minus. The only thing that changes is that sign right there. But notice that the probabilities stay the same, right? We still have a 50% chance of going up, oops, and a 50% chance of going down. So let's think about what changed here on the Bloch sphere, right? Notice if you tried to write ket plus and ket minus using these angles, theta and phi, would one of them stay the same? So again, I'll repeat that question. If you look at ket plus down here and ket minus back here, is one of these two angles the same for both of those arrows? And the answer you should get is yes. Theta is 90 degrees for both of them. Because again, remember, theta is just going to tell us how far away from the North Pole we are, right? So in this case, 90 degrees. The only thing that's different between these two is phi, right? Phi tells us where we are around the equator. Now, this is the first point I want to make about how you can interpret theta and phi. Theta kind of gives you a representation of the proportion of 0 and 1. Okay, so all I mean by that is when you're looking at a quantum state, the only thing that matters for, are you in a 50-50 superposition of 0 and 1? Are you in a 75-25 superposition of 0 and 1? The only angle that matters for that question is theta. So I like to think of it as theta determines the proportion of 0 and 1. If theta is 90 degrees, we're 50-50. If it's more than 90 degrees, we're more toward ket 1. If it's less than 90 degrees, we're more toward ket 0. And that's going to be reflected in our probabilities. So another way of thinking about this is if you're in the northern hemisphere of the Bloch sphere, you are more likely to collapse to ket 0. If you're in the southern hemisphere, you're more likely to collapse to ket 1. And if you're on the equator, you're equally likely to collapse to ket 0 or ket 1. Okay. Now, there's one more piece of math that I want to show you here with the Bloch sphere. There are some points where I'm just going to tell you where they lie on the Bloch sphere. But if you wanted to work this out for yourself, there is a formula for it. And it looks like this. So maybe you've seen this before. Maybe you haven't. That's OK. But this is the general formula for any point on the Bloch sphere. So if I plugged in some value of theta and phi here, this gives me the vector representation for what that point is. And conversely, if I have a state like ket 0, for example, and I know its vector representation, I can use these formulas to kind of try and reverse engineer what those values of theta and phi should be. Now, just as a quick reminder, this e to the I phi thing, I mentioned it earlier and said I would come back to it. So let's come back to it. We learned about a thing called Euler's formula, which said that e to the I phi is, by some magic, exactly equal to cos phi plus I sine phi, which is a very surprising result, right? You have this exponential function, and somehow it gives you back cosines and sines with imaginary numbers in them, right? It's weird. But it actually has a very nice interpretation in terms of the unit circle. Right? If we put our real part on the x-axis, our imaginary part on the y-axis, then e to the I phi is exactly just the unit circle. And phi tells you how far around the unit circle you are. Okay, so this e to the I phi term here, it's kind of like a circular term, right? It moves you in a circle. And this circular picture, by the way, is exactly the circle in the middle of this sphere. I'm not going to go into too much detail about how that works, but if you're starting to see some connection between the e to the I phi circle and the circle around the equator, you're getting the idea. That is exactly how it works. In general, though, all you need to know on this slide is this formula. So I think there's some questions on the homework where you will be asked to translate from theta and phi to the vector representation, and then to translate from the vector representation back to theta and phi. And for all of those, you're going to use this formula. So somebody just direct messaged me with another question about the attendance quiz. I apologize for that. There's no attendance quiz question this week. So you should be able to just open the quiz and submit it without answering any questions, and that will mark you as present for the lab. So the XY, so somebody asks in chat, the XY axis is analogous to the complex plane. Yes, exactly. So the way that this actually works is you could relabel the x-axis. You could just call that real, call this imaginary. Now this part, by the way, if you don't follow this, don't worry. This is not required. This is just building even more intuition. You could relabel these two things. And then what you would get is a full picture of the relative phase of your quantum state. So what I mean by that is, suppose you start with phi equals 0. Phi equals 0 corresponds to 1 right on the real axis, right? So there's no imaginary part there. It's just positive 1 on the real axis. Every state with phi equal to 0, which as a reminder is every state falling on this line here, every state with phi equals 0 will have some form where the coefficient in front of ket 1 is just a +1. There's nothing else here besides the sign. If, on the other hand, we go to phi equals 180 degrees, so back here, and we look at every single state along here, that point is -1, still on the real axis, but now it's minus. And so every point on that line is going to have a minus sign here. But of course, you can have lines that are, partially imaginary. So if you had a line out here, for example, that's kind of like, that'll be somewhere down here on your complex plane. And so you would expect this coefficient here, whatever it is, to have a negative real and a negative imaginary part. So it kind of defines how imaginary your ket 1 is, right? Either it's fully real, it's fully negative, or it can be partially imaginary. It all lies on the unit circle in the complex plane. I'm not going to belabor that point too much because you definitely don't need to understand all of the intuition for the Bloch sphere. Like I said, at the end of the day, all you need is that formula. Okay. So as I mentioned, these are the ranges. So we're going to do one quick practice problem here just to show how this works. What are theta and phi for ket 0 and ket plus? Now, there's a few ways to do this. The first way I'm going to suggest you do it is to try and look at the Bloch sphere. I'll throw where these states are. So the green is ket 0. The yellow here is ket plus. And I want you to just practice thinking about which angles would lead to these 2 points. So don't use the formula just yet. Just think about what angles would lead to these 2 points. I'll throw up a Zoom poll, and I will let everybody give this a shot. So one person asked in the chat, what does the relative phase physically mean? Because I sort of said how theta is the proportion of 0 and 1. Phi is the relative phase. I honestly don't have a good answer for you. Relative phase is, if I had to point to one thing that differentiates quantum mechanics from regular probability, it's the relative phase, right? Because otherwise you could just describe everything as some probability in one state and some probability in another. The fact that we have this relative phase concept is what really gives us the power of quantum mechanics. What it means physically, though, is a longer story. And I honestly, I only have a good answer for one particular type of quantum computer, which is photonic quantum computers. Remind me to come back to that at the end of the lab, and I can give you a quick explanation. But I think the short answer is there's usually not a good way to visualize it, unfortunately. I think. I'm happy to be proven wrong, but so somebody else said in the chat, can we call the magnitude of e to the I phi another form of the Pythagorean theorem? Yes, exactly. So we talked about that in the previous lecture where we introduced e to the I phi. And actually, I'll try and remember to link to that lab as well in my follow-up email, just if you want to review that concept. We are not going to be talking about mixed states, no. Ask me about it at the end of the lab, though, once we're into the optional content, and I can spend a few minutes on it if you'd like. Okay, so over 50% have answered. I am going to go ahead and show how I would do this problem. So starting off with ket 0, right? That is the arrow pointing straight up to the top. Now, for this one, all we really need is for theta to be equal to 0, right? If theta is equal to 0, we're already sitting at the North Pole, and the meaning of phi, well, it almost doesn't have any meaning anymore, right? So this is actually a bit of a trick question. As long as you picked something with theta equals 0, phi could be any number you want. It could be 0, it could be, pi, it could be 3 pi by 2, whatever. The value of phi doesn't matter because, again, we're sitting at the North Pole as soon as theta is 0. Okay, so for ket 0, it should be theta equals 0. Phi can be anything, which is a little bit of a trick question. I apologize. Okay, for ket plus, we actually do have a unique answer. Oh, by the way, yeah, this is what I was referring to before when I said almost every point has a unique set of theta and phi that describe it. The only 2 points that don't are the north and south poles, right? So when theta is 0, phi can be anything. When theta is pi, phi can also be anything, right? But whenever theta is in between, you do have to worry about what phi is. Now, for ket plus, the way that I like to think about this is first I will figure out theta, right? So ket plus lies on the equator. Therefore, theta has to go around 90 degrees, which is pi by 2. And then next up, I'm going to move around the sphere as much as I need to. But here, notice, as soon as I drop down 90 degrees, that was ket plus. Don't need to move around anymore. And so phi here is actually going to be 0. Okay, so somebody says, what I find misleading is the fact that on the Bloch sphere, you use theta over 2 and not theta. Yeah, that is a good point. I'm not going to explain exactly why that is. Well, to be honest, you could define it differently. I think actually in pure math, you would be more likely to see just theta here, and the ranges would be a bit different. The way you would visualize it is a bit different. In physics, though, it's kind of just a convention that we use theta over 2. A little bit confusing, yes, but you'll get used to it. Okay, so somebody says, why, since theta changes from 0 to pi, but cos is not invertible on 0 to pi, but it is on 0 to pi over 2, so that for each angle, you get a unique value. Ah, I see what you're saying. I think I do anyway. So for every potential point you could get on the Bloch sphere, you might, okay, so if you're using math to solve these problems, right? If I gave you some crazy state, I don't know, if I gave you like 3/5, 4/5, for example, right? And I asked you to find theta and phi for this, the way I would do that is to start off by using the arc cosine function to find theta, right? Because the top element here doesn't have any phi in it. So I can just take the inverse cosine of 3/5, and I'll get some answer, right, for my theta. The only caveat here is you do have to make sure that your theta falls in this range. So it's possible that you do the inverse cosine and you get an answer that falls outside of that range. And in that case, you have to go back to the sphere and think a little bit about where your states are, right? You have to, because basically what could happen is you could end up getting a theta value that is negative, for example, right? So instead of going 90 degrees down, it would tell you, oh, go minus 90 degrees, right? Now, you basically just have to use your visualization skills on the Bloch sphere to notice that that's the same as going 90 degrees in this direction and then rotating phi 180 degrees, and you get to the same point. Okay, so even if you got an answer that was outside of this range, you might have to correct things a little bit. And it's sort of the same idea as, remember when we were doing polar coordinates and inverse tan sometimes gave you an answer that was incorrect? It's kind of the same idea here. Whenever you use inverse trig functions, you do have to be careful to make sure that your answer falls within the proper range. Okay, so I am going to keep going just because we actually don't have too much time left. And I want to talk about gates acting on the Bloch sphere. This part, though, is actually a pretty simple extension. So hopefully it shouldn't be too much more. Now, just as a quick review, so far we've seen single qubit states and visualized them on the Bloch sphere. In a quantum computer, ultimately, we want to be able to change states, and we want to think about changing states. Now, there's a quick example here, which I'm going to skip over for now, that describes at a very high level something called Grover's search algorithm. Very high level, but it's the general idea behind a very famous quantum algorithm called Grover's search. And it effectively justifies why we want to be changing quantum states. But for now, I'm just going to say, take my word for it. We want to be able to change quantum states to do quantum computations. So let's go back again and do a quick review. When we applied gates to states, we said that was the same as multiplying a matrix by a vector, right? So here I have ket 0. I pass it through the x gate, which as a reminder just flips it. So it becomes ket 1. And the way I show that in linear algebra is with matrix vector multiplication. So this is our matrix representing the x gate. These are our vectors representing ket 0 and ket 1. You can do this computation to figure out how the x gate affects a quantum state. But we just described how we can visualize the quantum states on the Bloch sphere. So let's go ahead and do that. So now we have two arrows on the Bloch sphere, and we are doing some gate to them in the middle. And my question to you is now, what exactly did this x gate do, right? How did we move from this arrow pointing up to this arrow pointing down? Now, there are a couple of valid answers here. The way that we want to think about it in quantum computing is as a rotation. Okay, so the way I get from this arrow to this arrow is by rotating all the way down to be pointing at the South Pole. Okay, so hopefully you can sort of visualize just taking that whole sphere, rotating it, or I guess don't take the whole sphere, but just take the arrow pointing up, rotate it 180 degrees, sorry, and then it'll be pointing down. So this is a common pattern with quantum gates. Every gate, and I'll mention this at the end too, because it's honestly a very interesting and powerful result. Every gate corresponds to a rotation of the Bloch sphere. So literally any single qubit gate, I should say. Any single qubit gate you can think of, X gate, Hadamard gate, we'll learn about the Y gate and Z gate and rotation gates. All of those, well, I guess rotation gates sound obvious, but even something like the Hadamard gate is a rotation. Every single qubit gate can be visualized as a rotation of the Bloch sphere. So let's do some practice with this. First of all, I want to generalize a little bit, right? So in the previous slide with this X gate, we were rotating by 180 degrees all the time. But of course, you could come up with an arbitrary gate that just rotates by some arbitrary angle alpha, right? So here we have a gate that takes ket 0 and rotates it by some angle alpha. Now, if alpha was 180 degrees, we would get back the x gate. But alpha could be something smaller or greater or whatever than 180 degrees. Now, this is what the matrix looks like for this calculation. It does have like imaginary numbers in it, and it looks a little bit scary. But if you needed to know the matrix representation for, say, like a 45-degree x rotation, you could just plug in 45 degrees in all of these spots, and you would get a matrix that gives you that rotation. Now, note that here, again, we have alpha over 2 instead of just alpha. Again, this is just, this is just a convention. Okay, so let's see. Somebody says, as far as I know, counterclockwise is taken as the positive direction. Correct. Yes. So all of our rotations here, you'll notice. So for example, alpha, we're rotating in the counterclockwise direction. You don't necessarily need to memorize that. You can always just come back and look at these diagrams. But yeah, counterclockwise is the convention. Okay, so what exactly do I mean by an x rotation? Good question. I mean rotation around the x-axis, right? So basically treating the x-axis as fixed and then rotating everything around that x-axis. Yeah. Oh, sorry about that. Yeah, so all of this is relative to rotations about the x-axis. Okay, now I will make a small technical note here, which is some of you, yeah, exactly, the YZ plane, which some of you might have noticed. And that is, if you actually plug in pi, a 180-degree rotation here, I mean, you can work it out, but in fact, what you end up getting is this, which, spoiler alert, is not equal to the x gate that I showed you before. Right? Now, this is actually okay, but it does require just a bit more explanation because the difference here is only a global phase. These things are related by a global phase, and so it doesn't actually matter, right? Again, global phases in quantum computing don't matter. So we would say that the x gate here is functionally equivalent to Rx of pi. Even though they're not the exact same numbers, they're only off by a global phase. Okay, so I'm going to keep going. These problems have very entertaining names. So the first problem we're going to look at is called taking Santa to see penguins, which basically means going from the North Pole to the South Pole, right? And the question now is, what should alpha be if we want to apply the Rx gate to 0 and end up in the state 1? So again, if we look back here at what our rotation does, it rotates by an angle alpha around the x-axis. So picture taking the whole sphere, sort of like, putting a stick through the x-axis and then spinning the sphere around that x-axis. How much would you have to spin it to move the North Pole to the South Pole? That's effectively what this question is asking. And this is going to be, at the end of the day, we'll have to rotate it a full 180 degrees, right? 360 would bring us back to the start, but if we want to bring the North Pole to the South Pole, that's only 180 degrees. So here, alpha equals 180 degrees, which equals pi radians. Okay, let's look at another problem. We'll call this one taking Santa to the beach, which means we want to start in the ket 0 state and end up on the equator, right? There's lots of beach destinations on the equator. So here again, imagine sticking, put a stick through a globe along the x-axis and spin the globe around. How much do you need to spin it to move this arrow down to this arrow? Okay, so again, I'll give you a moment to think about this. Now, I like to just draw these things out personally. So if I'm trying to go from the yellow arrow to this final state, on the beach, so to say, that rotation is going to be 90 degrees, right? You have to rotate the whole sphere 90 degrees to get the arrow in the right location. And that's pi over 2. Okay. So far, so good. I wanted to say something on this slide. Okay, I kind of forget. My apologies for going a little bit over time. These are the last couple of problems that we're going to go over, though. Okay, let's look at another example. This one is called the Y gate. So this is something we haven't seen before, and it doesn't really have as nice of an intuition as the X gate. But if we look at what it does to ket 0, it actually does the same thing. It brings ket 0, and it rotates it 180 degrees down to ket 1. But now, instead of rotating around the x-axis, it is rotating around the y-axis. Maybe I'll try and draw that a little bit bigger. So we're going around the y-axis. Now, again, you can picture, like, take a ball, stick a skewer through it, right, along the y-axis, and then rotate it 180 degrees. The top point of the ball will move down to the bottom. And that's exactly what we see here. But just like the X gate, we can generalize this, right? We don't necessarily have to rotate 180 degrees. We can rotate an arbitrary amount beta. Now, this drawing is, it's hard to draw three-dimensional things in only 2 dimensions. So I will be the first to say that this is not totally clear what it's saying. But basically, we're starting up at the top, and we rotate some amount beta. Let me see if I can hand draw this relatively well, maybe. It's going to be tough. Something like that, right? So this line is intended to be a slice, like we talked about before. And beta is going to move us along this slice, right? So beta is just that angle there. And as we move down the slice, beta gets larger and larger. We need animations for this. That would have been a great idea. I agree. Actually, maybe for next week, because obviously I don't have them ready right now. But for next week, I'll make a note of that and see if we can get you some animations. Okay, so here is the matrix for these kinds of rotations. Again, you can just plug in some angle beta that you want to rotate by, and that's how you get a matrix for the rotation. Okay, so let's do another one of these problems. What is beta if we want to go from ket 0 to ket 1? So again, all we're asking here, try and forget about the matrix and all this complicated stuff. It's just a rotation. You're rotating a sphere by how many degrees to move the top down to the bottom, right? So somebody says pi, that is going to be correct. It's going to be a 180-degree rotation to go from the top down to the bottom. Okay, so we're going to do another question here. What is beta if we want to go from ket 0 to a final state 1 over root 2 ket 0 plus ket 1? Now, this looks complicated, I agree, but I would just remember that this here is equal to ket plus, and we know where ket plus is on the Bloch sphere. Think about the Stern-Gerlach experiment. Think about where ket plus should be and how much you need to rotate to get there. So I'm going to throw up a Zoom poll, and I'll wait until about 50% have answered the question, and then I'll go into it. Okay, in the meantime, I am going to just look at questions. We very well might send you all a 3 blue 1 brown video. Actually, I'll probably do that, to be honest. 3 blue 1 brown is great. I don't know if he has a video relevant to this, but I'll take a look. Okay. So somebody asks, how do we account for the angle, alpha or beta, when actually applying a gate on a state? So if you wanted to do this, if you wanted to figure out, how a quantum state changes with a particular gate, you would have to construct this matrix, right? So if I had beta equals, I don't know, pi by 3, and I wanted to know what that rotation does to a qubit state, I would just plug in beta to all of these different sines and cosines. You would get some matrix out, and then you would just do matrix vector multiplication, just like we learned. So that's where these formulas, these matrix formulas I'm giving you, that's where they're actually helpful, is if you ever had to do matrix vector multiplication on this. I think for the homework, at least, you won't have to do that. I think it's more about just looking at the Bloch sphere and mainly dealing with states, but these are good to know. Also, please share the poll results. Yes, sorry, I forgot to do that before. I will do that. How do we derive the sine and cosine matrix? I will not be going over that. For now, we'll just say that you take them for granted. I'm not sure if I can give like a high level explanation. Oh, okay, there you go. So the lecture, somebody says the matrices are constructed in this week's lecture by Amir. So I guess there you go. Yeah, I don't know how exactly they're constructed. I think I've always just taken them for granted. Okay, so more than 50% have answered the poll, and I will go ahead and share those results. So it looks like most people are getting the correct answer here, it turns out, which is going to be pi over 2. So the key thing to notice here is we visualized where our states are, right? We visualized where ket 0 is, and I gave you sort of an implicit hint here. You can visualize where ket plus is. And then I think the best way to do this is just think about what rotation you need. Try and visualize in your head rotating this sphere. You need to rotate it 90 degrees to get to this final state. Okay, last example, I promise. I know we're going quite a bit over time. I do apologize for that. The Bloch sphere takes quite a while to get used to. So the last example is the Z gate. And the Z gate is, it's technically no different from the others, but it can cause some confusion because if you applied a Z gate to ket 0, nothing happens, right? You can go ahead and do this matrix multiplication for yourself if you want, but applying the Z gate to ket 0 just gives you ket 0 at the end. Now, as you might guess, the reason for this is that now we're rotating around the Z axis. And so something that sits on the Z axis, if I put a skewer through my globe and I rotate it, the only thing that doesn't change as I'm doing that rotation is stuff on the axis, right? So here, ket 0 is on the Z axis, therefore it does not change. Now, states that are not on the Z axis do change, and you can change them by an arbitrary angle phi. Or sorry, this one is gamma. So again, here, gamma just measures how far you want to rotate around the Z axis. The matrix for this is the following. Okay, so again, you could just plug in gamma here, and you would get the matrix representation. Again, though, I don't think you should need to use this all that much. Instead, we're going to have one last concept question. This one is definitely the trickiest. But again, my advice, first visualize where your start and end states are, and then try to visualize how the sphere rotates to get there. So the question is, what is gamma if we apply the RZ gate to ket plus, and we want the final state to be ket minus? So again, visualize ket plus, visualize ket minus, and third step, visualize how much you have to rotate. Again, here we're doing a Z rotation, which just means that we're rotating about the Z axis. So picture sticking a skewer straight down through your sphere and spinning it like a globe. Okay, actually, I'll go ahead and throw up a poll for this. Sorry, I should have done that sooner. There we go. Throw your answer in the poll. Yeah, so one person points out it's easier for my visualization not to rotate the whole sphere, but instead just the vector on the sphere. That's a good point. So as we're talking about these different transformations, I would actually recommend that way. I would recommend trying to hold the sphere, stationary and think about rotating just the single vector. I would agree that that's more helpful. I think the way I've been saying it is rotating the sphere, which is perhaps not the most helpful. So that's a really good point. So somebody said, I don't quite understand the essence of the Y rotation. Could you please explain again, differentiating it with the X rotation? Yeah, absolutely. And actually, I'll do it with the Z rotation too, because all three of these are similar in that they are rotating by a certain angle around a certain axis. The only thing that's different is the axis around which you're rotating. So the Z rotation gate, rotates our states around the Z-axis. The Y rotation gate rotates our states around the Y-axis, and then the X rotation gate rotates them around the X-axis. You would be correct to point out that some of these rotations can appear to be identical with certain initial states. So we saw that with the Y gate, right? Where if you start off in ket 0, sorry about that. You start off in ket 0 and you do a 180-degree rotation. It doesn't matter if you rotate around the x-axis or the y-axis, you get the same answer, right? But the answer might be different if you started at a different state or if you rotated by a different amount. They are different rotations because they rotate about different axes. Okay. So that is our last concept quiz. I will quickly show how to do this. So again, like I said, visualize ket plus, then visualize ket minus. So again, here we've given you a bit of a hint. Ket plus is on the plus x-axis. Ket minus is on the negative x-axis. And so if we are rotating around the z-axis, how far do we need to go? 180 degrees, which is pi radians. So the correct answer here was pi. And I'll go ahead and share those too. Yeah, I absolutely agree. So somebody says it might be helpful to have certain plane views. There's a lot of different ways to visualize this. I think animations, plane views, all that kind of stuff. I will see if we can get some of that in next week's lab. Okay, somebody asks, how do you remember these various symbols and the corresponding axes? That's not a actual convention as far as I know. Like alpha, beta, gamma corresponding to X, Y, Z. That's not something I would try and memorize at all. It's just whenever you have a rotation about this axis, we're just using a variable to represent the angle. That's all. Okay, so that brings us to the end finally. I really apologize for going over time. So some key takeaways. This is the final slide that we'll talk about. The Bloch sphere is used to represent single qubit states, right? So again, every single qubit state is a point on the sphere, on the surface of the Bloch sphere. And every point on the surface of the Bloch sphere relates back to a quantum state. So there's this nice correspondence between the two. Applying a gate to a single qubit is equivalent to rotating the qubit on the Bloch sphere. So that's all of these practice questions we've been doing, rotating things around different axes. Every quantum gate is related to that same idea. Every single qubit quantum gate, that is a technicality. All of this stuff only works with a single qubit, but it's still very helpful. Every single qubit gate is a rotation of the Bloch sphere. Now, the final point here is not at all obvious, but it's really interesting. The rotation gates along the X, Y, and Z axes, that one's fine. Okay, whatever. what I really want to talk about is the second point here. By combining the Rx, Ry, and Rz gates, we can make any arbitrary qubit transformation. So what that means is, you can picture infinitely many different ways of rotating a sphere, right? You don't have to rotate it around X, Y, or Z. You could rotate it around some other random axis, right? But any rotation you come up with, in fact, any single qubit gate can always be sort of broken down into X, Y, and Z rotations. How to do this is definitely beyond the scope of this course, but it is a really neat result, right? You can always break down any rotation of the sphere into rotations about these three axes. Okay. So I am at the end now, finally. Just to give a quick preview of what's coming up. Next week, we'll be doing the IBM Quantum Experience. So for this, you need to go ahead and create an account. There are instructions on Canvas for how to do that. So make sure you go ahead, create your account this week, just so we have time to troubleshoot if anything goes wrong. And then in the following week, we're finally going to start talking about Qiskit, which is the language you use to program a quantum computer. And that's what we're going to be spending sort of the last bit of the course on, is actually talking about programming quantum computers. A few further readings and resources. There are a few of them here. Like I said, I will try and I'll try and add in a few more things for next week that help us with visualization of rotations on the Bloch sphere. And that is it. Woohoo, only 20 minutes overtime. Yikes. Okay, I'm going to relaunch the concept quiz just to see how people are feeling now after the lecture is over. And I will see if there's any questions I can answer. I need a high-level phase explanation. Do you think EMT2? I don't know what EMT2 in physics is. But I think the phase explanation, I think the best way to visualize it is with the Bloch sphere, because relative phase is just that angle phi, right? So remember, theta gives you the proportion of 0 and 1. Phi gives you the relative phase. What the relative phase means in physical terms, I promised I would get to that at the end. I will. But generally speaking, I think it's sufficient to picture the phase as just how far around the equator you are, which is just that angle phi. I just realized that the R gates must stand for rotation. Yes, that is correct. So R sub Z just means rotation around the Z axis, and so on for the other axes as well. Yeah, okay, so I'll make a quick list of things. I want to talk a bit more about the physical interpretation of phase. I will also go back to the search algorithm, Grover search, for a few minutes. I don't remember if there's anything else I promised to do. Oh yeah, mixed states, thank you. Mixed states. Okay. Are there anything else? Good one, best, awesome, thank you. Okay, so what I will do from now until however long it takes me is these three things, and then I will also do the bonus content, which is a little bit more about modes on pianos and violins. So those are the four things we have coming up, but the required section is 100% done. So feel free to sign off now if you would like. Again, these things are all recorded, so you can always come back and watch at a later time. So thank you all for coming out. My apologies again for going so far over time, but I do hope this was helpful. Okay, so let's go ahead and start doing some of these. Physical phase, that's the first one I will cover. Now, as I said before, just as a disclaimer, I know this to be a pretty challenging thing to actually visualize and come up with a physical explanation for. Relative phase, if I had to point to one thing that made quantum mechanics strange and contrary to classical beliefs, it would be relative phase. So by its very nature, it's hard to come up with a physical analogy in our real world. I'm going to try and give you one explanation, though. So one area where quantum mechanics is used is in describing the polarization of photons. So I know we haven't talked about this, but basically a photon is a light wave, right? So when we picture light, we know that light travels in waves. And it would be really nice if I had an animation right now, because this is going to be very hard to draw. Basically, though, as a light wave travels in a straight direction, there are two different waves oscillating. There's going to be one that oscillates like this in sort of the vertical direction. And then there's going to be another one that oscillates. Oh, yeah, this is really hard to draw. Shoot. Okay. How else can I show this? So suppose that my light wave is going along the x-axis, right? So I'm shining a flashlight, over here, and I'm shining it along the x-axis. There are actually two different waves traveling here. Sometimes you'll hear light referred to as electromagnetic radiation, right? EM radiation. The reason for that is because there's an electric wave and a magnetic wave, okay? Now, one way you can visualize this is, so that's the x-axis. Our z-axis is going to come up here. Our y-axis is going to come over here. One of those two waves, like for example, the electric wave, is going to go up and down in the xz plane, and the other one is going to go up and down in the xy plane. Okay, so what that would look like is one of them would oscillate up and down in the xz plane, right? So again, if I drew xz, the wave is going to travel like this. And suppose that's our electric wave. The other one, the magnetic wave, is going to oscillate in the xy direction. So notice both of these waves are traveling in the x direction, but the coordinate in which they're oscillating is different. One of them is oscillating in the z plane, one of them is oscillating in the y plane. Okay. Now, there are really good visualizations for this. I really wish I had one of them, but you'll just have to kind of try and picture there's one sine wave here that's vertical, and then there's another sine wave that is horizontal and kind of intertwines with the other one. Okay, so one way that we describe polarization with photons is by the direction in which these waves are pointing, right? So here, my electric wave is perfectly along the z-axis. So we might say that it's vertically polarized. Whereas if my electric field was along the x-axis, we would call it horizontally polarized. And these are just two types of light. We won't get into exactly how that's useful. But the basic idea is you can describe light polarization as being where that electric field is. Is it along the z-axis? Is it along the y-axis? Is it somewhere in between? So on and so on. So that is effectively the proportion of ket 0 and ket 1. In this case, vertical polarization, which we often do as ket V, is equal to ket 0. And horizontal polarization, which we do as ket H, would be ket 1. So if I have a light wave where the electric field is on the z-axis, that would be ket 0. If the electric field is on the y-axis, if the electric field is along the y-axis, then it would be horizontally polarized and ket 1. I'm realizing now this is quite a long explanation. I didn't realize it was going to take this long. But anyway, in this case, the proportion of 0 and 1 is basically just where that electric field is. Is it along z or is it along y? The relative phase in this case is whether these electric and magnetic fields are offset from each other. So the way I drew it here, both of them start off by going up, right? And then they sort of keep in sync with each other. But what if, for example, the magnetic field started off by going down? We would call this out of phase. Okay, and this is sort of where the term phase originates from. Here, the phase difference is 90 degrees. I won't get into why that is. And so the state represented by this would actually have a 90-degree rotation, a 90-degree rotation in the complex plane is the imaginary variable I. So in photons, when you're talking about polarizing photons, relative phase just means how aligned the electric and magnetic fields are. Okay, whereas the proportion of 0 and 1 has to do with whether the electric field is along the z-axis or along the y-axis. So yeah, this is, I think, the best explanation I can give for a sort of physical, how do things work of relative phase. It's not at all straightforward, though, as you can tell. It took me like 5 minutes to barely even scratch the surface on this. So relative phase is very, very difficult to come up with a physical representation of, I think, in summary. My Pictionary skills are being tested. I think I failed, unfortunately. Okay, so that's the first question. I will try and throw in a resource for that as well when I follow up. Okay. So one person says phase is between X and Y of electric field, I think, not between E and B. Oh, that could be the case. I am also not 100% confident on what I just drew. Some of my conventions might be wrong, but the general idea is definitely there. Okay, so let me see what I need to send. Visualizations, maybe from 3 blue, 1 brown. Lecture on Euler's formula. And I will also try and find a resource on what relative phase is in polarization. Okay, second one I'll do is to quickly go back and review Grover's search. So let me go back to that slide. Here we go. Okay, so I just glanced over this when we first went over it, but I'm going to read through it and go over it in a bit more detail. Now, our example here is that we're searching for a name in a list, right? So, for example, suppose I just give you an unordered list. I give you a list of 10,000 people that live in my neighborhood, for example, right? Not in any particular order. And you want to find out if your friend lives in that neighborhood, right? So you have one particular name you're looking for, and you don't know whether it's in this list. How would you find it? Well, initially, we have no idea where the name is, right? So each entry in the list, one way to think about this, is that each entry in the list is equally likely to be the name we're searching for, right? Our friend could be the very first one, could be the second one, could be the 500th, the 5,000th, it could be the 7,500th, whatever. Our friend's name could be anywhere in that list. And so the way we'll describe that is by saying our list is in a quantum superposition where every single state has an equal chance of being observed. So instead of just having ket 0 and ket 1 here, we're assuming that we have a system with many more qubits where we can be in any of these 10,000 states or any superposition of those 10,000 states. Now, at the end of our search algorithm, we want the states of the qubits to be such that there is a 100% or close to 100% chance of observing our friend's name, right? So we start off with something where there's a very small probability that each of the names is the one we're looking for. And we want to transform that qubit into something where there's effectively 0 probability of everything and then 1 probability of finding our friend's name. And this is effectively how Grover search works. It starts off with an even superposition over all possibilities, and you do successive transformations to get it closer and closer to this ultimate goal state. So for example, let me just redraw this over here. We start off in an even superposition, right? So some small probability of finding ourselves in any of the names in this list. And slowly we will apply some quantum gates, and I won't get into exactly what those gates are, but we'll slowly apply gates that start to pull out the one name we want. And as we continue applying these gates, the other probabilities will get smaller and smaller, and the one we want is going to get bigger and bigger. So this is sometimes called probability or amplitude amplification. And all that means is that you have the one state you want, and you're gradually amplifying it to make it different from the rest of them. And eventually, after you do this a whole bunch of times, you'll have virtually zero chance of seeing anything except the name you want. So that's effectively how Grover search works at a very high level. Okay, so let's go back. What else did I want to say? Grover search. Okay, mixed states. Yes. So number one, I guess I'll just clarify here, mixed states, not part of the course. So if you don't understand this or don't want to listen to this, that's totally okay. We are not going to need mixed states for anything we do here. The short story is that everything we've talked about so far is what are called pure quantum states. So even though they can be in a superposition, they can always be described by a single vector, right? By a single quantum state vector. A mixed state is what happens when you have some classical probability mixed with your quantum probability. So when you're in a superposition, there is some quantum probability that might give you a 50-50 chance of being in ket 0 or ket 1. But if you, for example, flip a coin, that is classical probability, right? There's no imaginary numbers involved, right? There is no entanglement involved. There's no interference involved, right? None of these things. It's just a clean 50-50 probability of being in heads or tails. A mixed state is what you get when you combine these two things. So suppose I wanted to do a quantum computing calculation. I wanted to apply a gate to a quantum state that I knew was either in the state ket 0 or the state ket plus. And each of these had a 50% probability. So basically what's going to happen is, you would come up to me, I flip a coin. If it's heads, I give you ket 0. If it's tails, I give you ket plus. You don't know which one I'm going to give you because I'm just going to flip a coin. But either way, you're going to try applying a Hadamard gate to it, for example, right? We don't really know. I mean, you might be able to think about for yourself how you might do this math. But there is a structure around it called mixed states in quantum computing. The cool thing about mixed states, though, with Bloch sphere is that today we talked about points on the surface of the Bloch sphere. And it turns out that, as I said, every point on the surface of the Bloch sphere is a pure quantum state, right? Every point on the surface of the sphere is a quantum state. Points on the inside of the sphere are mixed quantum states. Okay, so anything that's not on the surface, but somewhere on the inside of the sphere is going to be one of these things where you have, essentially a coin flip, and then you decide what quantum state you want. So it's kind of a cool mathematical trick that you can still represent even classical probability using the Bloch sphere. You just have to go inside of it instead of on the surface. Okay, so before I go into the bonus stuff, let me just take a quick look at the chat. Okay, let's see. Oh yeah, so somebody asks, if we have two people with the same name, how do we work out the amplification? So yeah, what would happen if you had two people with the same name is you would get two of those states that gradually get higher in probability, right? So instead of narrowing it down to only one and everything else has 0, you would have two, and maybe each of those has 50% while everything else is 0. So you can totally get that case. The name for it, if you want to look this up more, it's called amplitude amplification, is that process of sort of gradually pulling out the proper name. It's mathematically quite involved, just as a fair warning. The idea is simple, but the math starts to get more complicated. But yeah, it's called amplitude amplification. Yes, this is entirely optional content, just to be clear. So if you needed to head out, you can head out. polarization. Okay, can we discuss more about the imaginary part of the Bloch sphere? What does it actually mean in terms of the qubit? So I have two answers to this. The first one is, physically speaking, it's hard to describe, right? I tried to do it with photon polarization. It's much more difficult even to describe, though, in something like an electron, right? What it means mathematically, though, is the imaginary part. Actually, let me just read your question again to make sure. The imaginary part of the Bloch sphere. Okay, so the entire imaginary part of the Bloch sphere, let me go back to a picture of it. Here. Okay, so essentially everything on the xz plane. So if you try and picture this whole xz plane, everything on that loop has only real numbers in it, right? And again, the reason that is because the xy plane is effectively the complex plane. And so everything on the x-axis is going to be just real. And so if I wrote my quantum states, those would all be things that look like, alpha ket 0 plus beta ket 1, but alpha and beta would both be real numbers, right? That is all of the states lying on that loop. As soon as we allow ourselves to move off that loop, so for example, somewhere over here, we are going to start seeing imaginary numbers in our quantum state. In particular, alpha is going to stay real, but beta now is going to be complex. Okay, so as soon as you move off of that, you're going to start getting an imaginary component. Now, you can see this mathematically as well. If we go back to the formula for the Bloch sphere, this guy. So you'll notice the top element here, which, again, another way of writing this, by the way, just if this wasn't clear, it's entirely equivalent to write this as cos theta over 2 ket 0 plus e to the I phi sine theta over 2 ket 1. Right? I'm just writing it in terms of ket notation, right? So notice here, the coefficient on ket 0 is always going to be real in Bloch sphere world, right? There's no imaginary parts there. No matter what theta is, cos theta over 2 is always going to be real. The part that can become imaginary is this e to the I phi, right? And so you can picture that, as I said, as a unit circle on the complex plane. If you are somewhere on the x-axis, it will be real. But as soon as you move off the x-axis, you start getting an imaginary part in that ket 1 term. Hopefully that's helpful. And I guess, yeah, just to double back, the physical interpretation of what that imaginary number means, definitely beyond the scope of this course. I wouldn't even say that I fully understand what the imaginary part means in a physical sense. So somebody says, is a mixed state something like conditional probabilities? Yeah, exactly. It's sort of talking about having some classical probability, so basically some coin flip associated with your quantum states. So not only can you be in a superposition, you can also have a coin flip to figure out which superposition you're going to be in, right? And that's what a mixed state is. What benefits does classical probability, including this info, have? So where mixed states are actually used in research and that kind of thing is basically whenever you have, I mean, some uncertainty about what you're looking at. So one easy example that we've actually seen is the Stern-Gerlach experiment. Now, I won't go through the exact math on this, primarily because I don't remember it. But with the Stern-Gerlach experiment, you would have something like an electron gun, right? And these electron guns, they could shoot out electrons that are in any different spin, right? They could be spin up, they could be spin down, they could be spin right, they could be spin left. We don't know, right? In a lot of the problems we've done, we assumed that the electron gun produced only spin up electrons. The way electron guns work in real life, though, is they just spew out random electrons with spins in all different directions. And so the way you actually represent one electron coming out of an electron gun is using a mixed state, right? Because each of the spins is a superposition, but there's a random, which spin it ends up in is random chance. So which spin you end up in is the classical probability. Once you know which spin you're on, then there's going to be some superposition within that spin. Okay, yeah. So does the mixed state have an effect on single quantum gates or combined quantum gates? Not sure I understand that question. Let me see. Why do we need to locate this qubit on the Bloch sphere? So the Bloch sphere is entirely optional within quantum computing. You, technically speaking, never have to learn about it. You could just use matrices and vectors all day. But it's easy. It tends to be easier to think about problems and visualize things using the Bloch sphere. So it is just a tool to help. It doesn't really, technically speaking, it's not required. Okay, so somebody asks, if we can access the Bloch sphere from the inside for classical probabilities, why don't we connect the states that are in superposition from the outside of the surface of the sphere? Good question. I actually don't really know what, I'm not really sure what the points outside of the sphere would represent in this case. They might be useful for something, but I'm not sure what. So I think, the core thing to remember here is the surface of the sphere is pure states. The inside of the sphere is mixed states. The outside of the sphere, I've never heard of that being used, but it'd be interesting to know what, if it has any use. Yeah, so somebody says mixed states happen to be used really often. Uncertainty is a big part of working on real life problems. Totally, right? And I have to say, like, when you're working on quantum experiments, you almost always are using mixed states because your instrument, like, the generators you use to create electrons or to create photons or whatever, there's some uncertainty associated with them. You'll never be 100% certain with what they're generating. And so mixed states is how you model that, how you model sort of real world uncertainty. Okay, so somebody says, is the mixed state the same as a superposition state? No. Actually, I think there was a bit in one of the labs that we did on this, on the difference between classical and quantum probability. I'll see if I can dig that up. I don't remember exactly what the explanation was, but they are different, right? So classical probability, like I said, it can't, it's kind of like, think about the double slit experiment, right? When you had a superposition of going through the left and the right slit, there's interference, right? Those two superpositions interfere with each other. When you have a coin flip, there's no notion of interference between heads and tails. It's just a clean 50-50 shot at which one you get. So the big difference is that superpositions can interfere with each other. They can become entangled, all that kind of thing. They have imaginary numbers, right? All of that doesn't exist in the world of classical probability. So that's high level what the difference is. Okay, so then there's some speculation on what outside of the sphere does. It's not immediately clear to me, but yeah, there might be a good explanation for it. I'm just not sure what that would be. Okay, so final piece I want to do then is the bonus on modes, because this part is kind of fun. We're going to return to the example we talked about last week, which was plucking a string, right? Now, when you pluck a string, you can, of course, pluck it in a shape that is not any of the modes, right? So here the modes would be like 1, 2, 3, and so on. But you can pluck it in a shape that is not exactly one of those modes. What we learned, though, is that you can reconstruct this pluck by adding together a whole bunch of these fundamental modes. And we had a nice little sequence of animations last week to show what that looks like. Now, I want to show just one more example on this topic. we're going to listen to two sound clips of a piano and a violin. Now, I'm going to tell you right up front, both of these are playing the same note. Okay, it's an A40, 440 hertz. It's called A. It's the same note that both of them are playing. I want you to listen for any differences, though. See if you can tell the difference between the piano and the violin. So hopefully this works.
Right.
Did everybody hear that? Hopefully. Yes. Oh, good. Okay. So that's the piano. Let's go ahead and do the violin. Okay. So again, these are both playing the same note, and you should be able to sort of hear that the pitch is the same. But hopefully you can also tell there's some differences, right? We can intuitively tell when you're listening to a piano versus when you're listening to a violin. So my question to you then is, why is that the case, right? If both of these are the same notes, if they're both 440 hertz, the sound waves look the exact same, right? Both of the sound waves are going to vibrate at 440 hertz. So how is it that you can tell any difference between the two instruments? So one person already took a guess. They said that the piano is more pure. That's a very good guess. That's along the right path. So we can listen one more time.
Right.
That's the piano, and then violin. There we go. So one person just said overtone distribution is different. If you don't know what that is, that's okay. That happens to be the answer. But yeah, so there are some differences just in the sound files that we used. So one of them is longer, some of them have a bit more background noise. But the fundamental difference that allows you to distinguish between a piano and a violin is not actually the 440 hertz. It's everything that comes above that. So,
Right.
Oops, there we go. So what we're looking at here is two charts of the piano's note and the violin's note. And these you can generate just with software. We won't go into exactly how, of course, but this is what you would see. And what we're looking at here is the intensity of frequencies at each level of frequency. So you can see at the very bottom, this is about 440 hertz, right? And that's the fundamental note of our A. But it turns out that is just the first mode, right? That 440 hertz is just the first mode of vibration. What makes these two instruments sound different is all of the higher modes. So it turns out that all of these different spikes here correspond to the second, third, fourth, and there are a few more after this. They correspond to all the different modes. And you can tell by looking at this that, for example, the third mode on the piano is louder than anything else. What you hear primarily is actually the third mode of vibration. Whereas on the violin, the third mode is almost not even there, right? So when you try and think, when you can sort of hear the difference between these two instruments, what you're hearing is, as one person said, overtones. It is these higher order modes that make the difference between a piano sound and a violin sound. So just a couple of key takeaways. As I said, the same note played on the violin and the piano are different because the relative amplitudes of the different modes are different, right? So again, we were looking at here the relative amplitudes of the first, second, third, fourth modes, and those are different between the two instruments. Now, by changing the relative contribution of the eigenstates in a qubit, we can again change the qubit state. So in the world of quantum mechanics, if you had two qubits with different amplitudes of their various modes, those would behave differently in physical experiments, just like how you can hear a difference between the piano and the violin. So I really like this analogy of using sort of musical instruments to talk about eigenstates and modes and superposition and all that kind of stuff. hopefully this helps illustrate that idea just a little bit more. Okay, that's all I wanted to talk about on this. So I think that pretty much hits the end of all the stuff I said I was going to go over in the questions. So does anybody else have any other questions? Yeah, it's super cool. So the conclusion is one note is more piano compared to, yeah, one mode. I think perhaps you meant to write one mode. Exactly. Like that third mode that we saw turns out to be a defining characteristic of what a piano sounds like to us, right? That's what we've been trained to hear. The last result is still not, oops, what did I just do? The last result is still not very clear to me. So this honestly doesn't have, like I haven't given a super clear connection back to quantum computing. The very last piece I said here though, with changing the relative contributions of eigenstates, basically all we're saying here is, if our piano and violin were qubits, what we would do is we would label the first mode as ket 0 and the second mode as ket 1, and then we would ignore everything else, right? So this would be ket 0, this would be ket 1, and then we ignore everything else. And so if I were to write some kind of, very sketchy notation here, this ket 0 for the piano is maybe about 1/4 probability. And the ket 1 is maybe like 3/4 probability, right? Something like this. So this would be the quantum mechanics way of writing out what a piano sounds like. And then the violin is going to be, I don't know, maybe like 60% ket 0 and 40% ket 1. Something like this. Now, just by looking at these two expressions, you can probably tell that this one over here is different than this one here. Exactly how it's different is besides the point. It's not too important. But that's my point here is just to say that the difference between these two states is the reason we can hear a difference between what a piano and a violin sounds like. And it's the same idea with adding together quantum states. Changing the eigenstate is the same as changing the magnitude. Right, so the height of these spikes here is effectively changing the magnitude of those probability coefficients. If we take that analogy, does it mean that in quantum mechanics, the contribution of eigenstates is not equal? Ooh, I don't think so. So yeah, you're right. Like in this analogy, I sort of implied that the first mode, right, the 440 hertz A, is the note that we hear. And so it's kind of more important in a way. I honestly think the best way to relate that back to quantum mechanics is just to say, if you have a particular confinement, right, if you have a particular length of string or a particular size of confinement for your electron, you will always get these same modes, but you might get them in different proportions, right? And so here, you always get the same note, but because the different modes are in different proportions, the texture of the sound is different, right? And we can tell the difference. Cool. Okay. Marathon lab today, almost 2 hours. Thank you all for sticking it out right until the end. In the same confinement, exactly. Yeah, so somebody just clarified there. These electrons would be in the same confinement. That is correct. Okay, yes, to those of you going for dinner, have fun. To everybody else, good luck on the homework this week. Definitely go on Piazza if you do have any questions. But otherwise, I will see you next week for our first dive into the IBM quantum experience. It's going to be great. So we'll see you all later. Bye.